Welcome back, everyone. So, this session will be another interesting session based on the fundamentals of thermodynamics, which will be the basis for first law of thermodynamics and the important concept of internal energy and then enthalpy, and later for the working of internal combustion engines. So, please listen the lecture till the end, note down the important points. If you haven't subscribed yet, please do subscribe. So today we'll be discussing on energy and energy transfer. So all of you are aware what energy is, right? I think I have mentioned in my previous lectures what energy is. So thermodynamics is the science of energy, isn't it? Energy, energy transfer, and energy transformation. So first law of thermodynamics is another way of stating the law of conservation of energy. So first law of thermodynamics itself tells about energy. It's a statement about energy only, conservation of energy. So I don't need to reiterate what is the law of conservation of energy, you know. So there is a basis, first law is the basis for definition of the property known as total energy. So total energy, usually denoted by uppercase E of a system, it is a sum of all forms of energy that can exist within the system. Sum of all forms of energy. It could be kinetic energy, potential energy, or internal energy. We will define that internal energy later. So internal energy is that energy associated with molecular structure of a system. You know that each and every substance is made up of tiny particles known as molecules, isn't it? So the energy possessed by these molecules. So each and every molecule will be having energy of the form of translational kinetic energy, rotational kinetic energy, vibrational kinetic energy, nuclear energy, even potential energy. All forms of energy will be available or exist at the molecular level. So sum of all these forms of energy at the molecular level is termed as internal energy, and it is denoted by U, not E. E is the total energy of the system. U is the total internal energy of the system. That is a So here you can see the conversion or law of conservation of energy. When the vehicle is moving up, potential energy is increased. When the speed increases, automatically that energy is converted to kinetic energy. That's what it is shown here. So total energy of the system, as from the discussion so far, could be concluded as the sum of kinetic energy, potential energy, and internal energy in joules or kilojoules, and the change in stored energy of a system during a process. When there is some kind of energy transfer taking place, the change in energy, that is denoted by delta E. Delta stands for final state minus initial state. So delta E is the sum of change in internal energy plus change in kinetic energy plus change in potential energy. So kinetic energy as well as potential energy are at the system level and internal energy at the molecular level. Now for a stationary closed system, when there is a system which is stationary, not moving, the kinetic energy obviously will be zero. If it is closed system, there won't be any mass transfer, only energy transfer in the form of heat or work. So change in stored energy is identical to change in internal energy, or delta E is equivalent to delta U. Now there are two forms of energy transfer, right? We have seen in the discussion of different types of systems: open, closed, and isolated system. You know that energy can be cross the system boundary either in the form of heat or work. So if the energy transfer is due to temperature difference, that is termed as heat transfer. If it is due to the energy expended to lift a weight, that is called work. Or we can simply say, if there is no temperature excess, still there is energy transfer, obviously that will be work transfer. So these are the similarities between the heat and work. Both of these are not properties of the system. This will show up only at the boundary of the system. Or in other words, both of these are boundary phenomena, both heat as well as work. Usually these are known as heat transfer and work transfer. And the systems possess energy but not heat or work. That means these are not properties. Energy is a property, but heat or work are not properties but boundary phenomena. Both are associated with a process, not a state. Both are path functions, not point functions. All the properties are point functions, but since work and heat are transfer mechanisms at the boundary, there is no meaning in saying a system has got this much work or this much heat. That is meaningless to say like that. So both are path functions. So their magnitudes depends on the path followed during any process as well as the end states, obviously. So since they are path functions, they have inexact differentials denoted by delta, small delta. Greek symbol delta is employed, delta Q and delta W, not delta Q or delta W like this. It is small delta Q and delta W. Or you can write Q12. Never you should write as Q alone. Q12. It is a path function. It is expressed as a path function and it has meaning only in a process, Q as well as W. So coming to the sign conventions, when heat is added to a system, its thermal energy increases and it is positive. Heat transfer to a system is positive as well as work transfer from a system, if work is done by a system, that is positive, and the remaining are negative. When the heat is transferred out of the system's energy decreases and it is negative, and when the work is given to a system or work is done on the system by some external source, so work transfer is designated as negative. So that's all for today's session. So we'll meet in another session. Till then, it is goodbye.